Welcome to antenna as a component. In this video, we'll discuss about line of sight wireless communication and the Friis transmission equation. So, as per the title, the purpose of this slide is two things. First, to understand what is the ideal line of sight communication channel, and then we will derive the Friis transmission formula or equation which represents this channel. Line of sight or LOS communication is simply that the transmitting antenna and the receiving antenna can see each other directly without significant obstruction. So the characteristic of the ideal LOS channel are: first, there is a direct path between the transmitter and receiver without any obstacles. Nothing blocked the wave significantly. This is the first one. The second one is that there is a minimal multipath effects, means the wave propagating from the transmitter and receiver is a significant wave, come with say P1. So if there's another surface where the wave go and diffract or reflect or scatter on it, its power P2 is much smaller than this P1. The third characteristic is that there is a negligible ground reflection, because if there is a ground reflection, we need to have another model, which is the two-ray model. We cannot use in this case the line of sight. And why we need to do this one? Because if we have two antennas which have, of course, some line of sight, say arrive with power P1, and due to the ground reflection there is another power P2, this power will be close to the value of course still less than P1, but it's close to the value, and we need to consider this power also when we calculate the actual power received by the antenna. Finally, the antennas need to be stationary or quasi-stationary, because if the antennas are mobile, we need to consider something called Doppler effect, which we will cover in different course. So in short, to apply the line of sight model, our antennas need to see each other without any obstacle. There should not be any multipath effects, no ground reflection, and the antennas need to be stationary enough not to consider the Doppler effect. So if we are under the line of sight conditions, we can apply the Friis transmission equation or formula to relate the received power and the transmitting power. And this is the Friis transmission equation or formula, and it is just the value of the power received will depend on the of course the transmitted power, both the gain of that transmitting and receiving antenna, and divided by what's called the path loss. Before concluding this video, let's prove the Friis transmission formula. And in order to calculate the received power at a receiver, we need to know two things. One is the power density of the transmitter, and the second thing is the aperture area of the receiver, because we know that the power received is just the power density at the receiver terminal multiplied by the effective aperture area of the receiver. So from the transmitting antenna, actually we can calculate the power density from the gain equation, which we have proved in a different video. We by definition, G of the transmitter is just equal to 4 pi r square multiplied by the power density divided by the total power. If we reformulated this one for the power density, we will get that the power density at any distance from the transmitter. So if we calculate for r, which is the distance between transmitter and receiver, we will get it equal to just the total power multiplied by the transmitting gain divided by 4 pi r square. Then, if we look from the transmitting antenna side, we have learned that the receiving antenna or any antenna aperture area is calculated as lambda divided by 4 pi multiplied by the gain of that antenna, in this case the grx. Now we just need to apply this equation. Once we apply it and substitute by this value and this value, and just manipulation, mathematical manipulation, we can reach to our target equation, which is the Friis transmission formula. Finally, we are with the conclusion, and we have learned in this video about the line of sight communication, which assume that the transmitting and receiving antenna have an existing path between them and are stationary or quasi-stationary, I mean not mobile antennas. And there is also, for the other condition, is that there is negligible ground reflection and there is minimal multipath fading. And if these conditions are satisfied, we can use the Friis transmission formula in order to calculate the received power at the receiving terminal. In the next video, we'll discuss about the antenna losses and the generalized Friis transmission formula. Stay tuned.